Hello, fourth grade math friends. So remember back to the beginning of this chapter when we had those bugs, right? We needed to make sure that we didn't have any bugs trailing off at the end. And in order to do that, we made equal rows. And then we've been exploring that concept throughout the chapter. Today, we're going to work some more with that idea. Let's take a look by starting with this problem. Students are rearranging square tables to make one larger rectangular table. The students want to have several ways to arrange the tables. Should they use 12 or 13 square tables? So I understand in this problem that the students can either use 12 or 13 square tables and then arrange those square tables in different ways in order to make one large rectangular table. I'm going to use some counters to help me in order to make some equal rows to see what different ways I can arrange these different sets of square tables. So I'm going to start with the number 12. So I have 12 counters here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I'm going to see how many different ways that I can arrange them. And I know that those are going to be my factors of 12. And I'm going to keep track of them as we're working here. So the way I have my factors lined out right now, I have one row of 12. So I know that 1 and 12 are both factors of the number 12. Let's go ahead and split this in half and see if we're able to make 2 rows. And we see that we are able to do so. Right now I have 2 rows, and in each row I have 6. So I have 2 rows of 6. So now I still have another, this is another shape that my rectangular table could take, right? I could have this long rectangular table, or I could have a shorter rectangular table that's a little bit wider. Let's keep going. What about 3 rows? Let's see if we can make 3 rows with these 12 desks, and we can, right? We have 3 rows of 4. And we can try 5, but actually now that I'm thinking about it, we know that 5 is not a factor of 12 because it doesn't end in a 5 or a 0. And so it looks like we've finished up here. So we are seeing that we could arrange these desks in several different ways if we used 12 desks. Now, I want us to think about 13. So I've added 1 counter, and I'm going to go ahead and make another row where I can list out my factors, but instead of 12, we're going to list factors of 13. And I see that I could have 1 row of 13, and that would make 1 rectangular table. So I've got 1 and 13. Now I'm going to see if I can split it in half and make 2 rows, and I'm not able to do that because I've got 1 extra desk hanging off, and they want a rectangular shape, so that's not going to work. Maybe I could try 3 rows. And again, I've got an extra 1 hanging off at the end here. Well, let's try 4 rows and see what happens. Again, I've got this extra desk that's not fitting into my rectangular shape. I know 5 is not going to work because the number 13 doesn't end in a 0 or a 5. So here's what it looks like if I try with 5 rows. And so I'm finding that the only factors of 13 are 1 and 13. And so to answer this question, should they use 12 or 13 square tables? My answer would be they should use 12 tables because they can arrange the desks in several ways. And that's one of the things they wanted. They wanted to be able to arrange the desks in several ways. If I have 13, I can really only arrange it in one way, 1 row of 13, right? Or I could use my commutative property, and I know that I could switch this all around and do 13 rows of 1, but that's still not as many options as if I used 12 desks. So my answer to this question would be 12 desks. Now let's think about these numbers a little bit more. I'm noticing that 12 has a lot of different factors, right? That makes 12 a composite number. A composite number is a whole number greater than 1 that has more than 2 factors. As I look at the number 12, I definitely see more than 2 factors here. So that makes this a composite number, and that's what allows us to arrange these 12 desks in a lot of different configurations. The number 13 only has 2 factors, 1 and 13. That makes this a prime number. A prime number is a whole number greater than 1 that has exactly 2 factors, which are 1 and itself. And we know that's the identity property of multiplication, right? 1 times a number will be that number. So if the only 2 factors of a number are 1 and itself, and your number is greater than 1, then your number is a prime number. So we're finding that the number 12 is a composite number, and the number 13 is a prime number. Now, you might be wondering about the numbers 0 and 1. You might be thinking, well, are those numbers prime or are they composite? Let's think about the definitions of these numbers, these types of numbers. A prime number needs to be a whole number that's greater than 1 that has exactly 2 factors, which are 1 in itself. Is 0 greater than 1? No, it's not, right? So it couldn't be a prime number. Is 1 greater than 1? Well, no, it's not. It's equivalent to 1, but it's not greater than 1. So 1 is also not a prime number. Well, could they be composite numbers? Let's refer to that definition again. A whole number that's greater than 1 that has more than 2 factors. So again, I'm thinking, is 0 a whole number that's greater than 1? Nope, it's not. Is 1 a whole number that's greater than 1? Nope, that also is not. So 1 and 0 are 2 numbers that are neither prime nor composite.